Have you ever looked up at the stars and wondered, really wondered, what holds it all together? Not just the particles, but the deep rules governing everything. Today, we're doing a deep dive into maybe the most powerful framework we have for that, quantum field theory. Our plan is to journey through, well, the core ideas from a key textbook, pull out those aha moments, and give you a kind of shortcut to understanding the universe's hidden rulebook.
It really is amazing when you look at how this framework was built. It's not just describing, say, light or matter on its own. It's about unification, bringing forces together, and tackling these really challenging infinities that popped up in the math. We'll trace the path, from QED, quantum electrodynamics, through the electroweak theory, and even touch on QCD, the theory of the strong force.
Okay, let's kick things off with something familiar, or maybe seemingly familiar. Light. Before we had quantum fields fully formed, light itself was getting a radical rethink. Take us back. Planck, Einstein?
Yeah.
How did they start changing the picture?
Right. It really starts around 1900. Max Planck is studying black body radiation, and he proposes this, revolutionary idea. He suggested energy isn't emitted or absorbed smoothly, but in little packets. Quanta, like steps, not a ramp.
Discrete chunks of energy.
Exactly. Then, just 5 years later, 1905, Einstein takes this further. He argues that light itself is made of these particles, what we now call photons.
So light isn't just a wave, it is these particles, these photons. What does that actually mean for how light behaves?
Well, it's a huge shift. These photons, they're the quanta of the electromagnetic field, right? And they act like actual particles. They even have a specific amount of intrinsic angular momentum spin 1 specifically. It's part of their identity.
So this wave particle thing was real right from the start.
Oh, yeah. It was one of the first truly mind-bending ideas from quantum mechanics. And it wasn't just theory. The Compton effect showed it experimentally. Photons literally knocking electrons around like tiny billiard balls. It confirmed that particle nature.
Okay, so we have photons behaving like particles. And they interact with other particles, like electrons. Calculating that sounds difficult.
It is. Solving the full equations for interacting quantum fields is, incredibly hard. Usually impossible directly. But if the interactions aren't too strong, what we call weak coupling, there's a toolkit. Perturbation theory.
Perturbation theory. Breaking it down into simpler steps.
Sort of, yeah. You approximate the answer piece by piece. And the key visual tool for this, Feynman diagrams. Absolutely revolutionary.
Feynman diagrams.
Oh.
I've seen those little drawings, the lines and squiggles. What made them so special?
Before Feynman, the calculations were just pages and pages of dense math, really hard to keep track of. Feynman gave us this visual shorthand. You draw lines for particles, squiggles for force carriers like photons. You can see the interaction.
Like an electron spinning out a photon.
Exactly. Or two electrons exchanging one. It turned abstract equations into intuitive pictures. It wasn't just about calculation. It changed how physicists thought about interactions.
A whole new language, almost.
Pretty much. And they're used everywhere in particle physics now, not just in QFD. Super powerful tool.
Okay, that covers light. What about the particles that make up matter? Does quantizing their fields lead to similar insights or surprises?
Absolutely. Let's think about a field that's complex, meaning it has sort of two parts, like a real and an imaginary part mathematically. When you quantize that kind of field, the Klein-Gordon field, for example, which describes spinless particles, bosons.
Like pions.
Right, like the pi mesons. The math itself forces you to have pairs, a particle and an antiparticle, with opposite charges. So quantizing the field for a pi plus meson automatically includes its antiparticle, the pi meson. It's built in.
Particle-antiparticle pairs coming right out of the math for complex fields. What if the field isn't complex, though? Like for a neutral particle, say, the neutral pion, the pi.
Good question. If the field is real, just one component, mathematically speaking, like the field for the PO, then the operator for electric charge gives you 0. So electrically speaking, the PO is its own antiparticle.
But is it always about electric charge?
No, not necessarily. There are other conserved quantum numbers, these additive quantities, like hypercharge. Take the neutral K mesons, the K0 and its antiparticle, the K0 bar. They're both electrically neutral, but they have opposite hypercharge. So even without electric charge difference, they form a particle-antiparticle pair based on this other conserved quantity.
Fascinating. Okay, so we've got spinless bosons like pions.
Yeah.
What about the stuff we're really made of, like electrons? They have spin, right?
Right. Electrons are spin 12 particles. For them and other relativistic spin 12 particles, we use the Dirac equation. And this spin value leads to a really fundamental split in the quantum world.
Bosons and fermions.
Exactly. Particles with whole numbers spin 0, 1, 2, those are bosons, like photons or pions. Particles with half integer spin 12, 32, those are fermions, like electrons, protons, neutrons. And this difference in spin, it dictates completely different behavior.
And you mentioned something about second quantization being more elegant for handling particles and antiparticles with the Dirac equation. Less awkward than the old hole theory.
Oh, definitely. The whole theory was Dirac's original idea. He imagined the vacuum filled with an infinite sea of negative energy electrons. A hole in that sea would look like a positive electron, a positron.
Sounds a bit contrived.
It worked, but yeah, it felt a bit like an intellectual contortion, as the textbook puts it. Second quantization is more fundamental. You basically treat the wave functions themselves as quantum operators. When you do that for the Dirac field, electrons and positrons just emerge naturally from the mathematics. No infinite sea needed, much cleaner.
And it automatically includes the fact that electrons are fermions.
Yes, the math naturally leads to anti-commutation relations, which enforces Fermi-Dirac statistics. Meaning you can only have one fermion, one electron, say in any given quantum state. 0 or 1. That's the Pauli exclusion principle, fundamentally linked to their spin 12 nature. Crucial for why matter is stable and takes up space.
Okay, so the theories were getting incredibly sophisticated, but then physicists ran into a huge problem, didn't they? This wall of infinities.
Yes, a massive roadblock. As they tried to calculate more precise predictions, things went haywire. They were looking at radiative corrections, tiny effects from particles interacting with virtual particles that constantly pop in and out of the vacuum.
Like an electron interacting with its own field.
Exactly, it's self-energy. Or how virtual particle pairs in the vacuum can screen the electron's charge. That's called vacuum polarization. When they calculated these things using the existing theories, the answers came out infinite.
Infinite mass. Infinite charge. That can't be right.
Precisely. It meant the theory, taken literally, was predicting nonsense, a real crisis.
That must have been incredibly frustrating. You build this beautiful theory and it spits out infinity. How did they even deal with that before renormalization came along?
It caused huge debates, a lot of soul-searching about whether the foundations were sound. Some thought quantum mechanics might break down at small scales. But then came this ingenious, if initially controversial, idea: renormalization.
Renormalization. Okay,
Yeah.
How does that tame the infinities?
The key insight is, well, you never actually measure the bare electron, the theoretical point particle, before it's dressed by all these virtual interactions.
Right, you measure the real thing, interactions and all.
Exactly. You measure its physical mass, its physical charge. Renormalization is essentially a procedure to relate the infinite results from the bare calculations to the finite physical values you actually observe. You absorb the infinities into those unobservable bare parameters. It's like saying, okay, the bare mass calculation blows up, but we know the real mass is, say, 0.511 MeV. Let's redefine things so our predictions use the measured value.
Hiding the infinities in a way.
In a mathematically consistent way, yes. And in QED, something remarkable happens with charge renormalization, the observed electric charge that we measure. It turns out that its renormalization comes only from vacuum polarization, those photon self-energy effects.
Not from the electron's own self-energy corrections.
Nope. Or other vertex modifications. It's a specific consequence of the theory's symmetries, confirmed by something called Ward's identity. It shows a deep consistency.
And you do a similar thing for mass, right? Mass renormalization.
Yes, absolutely. The infinite bare mass gets replaced by the measured physical mass. It makes the theory predictive using real-world inputs.
So renormalization wasn't just a mathematical trick. It actually made QED incredibly powerful and accurate.
Phenomenally accurate. QED became what's called a renormalizable theory. That means its predictions are finite, and importantly, they don't depend on the specific, arbitrary way you initially handle the infinities, like imposing a cutoff energy.
The results are robust.
Very robust.
Yeah.
And the predictions, well, they are outstandingly successful. Things like the anomalous magnetic moment of the electron, this tiny correction to its magnetic field, and the Lamb shift in hydrogen energy levels. The agreement between QED predictions and experimental measurements for these is just staggering, some of the best in all of science.
Incredible precision, born from taming infinity. How do they actually do the math, though, if the intermediate steps are infinite?
They use clever mathematical techniques. One very common one is called dimensional regularization.
Dimensional regularization. Sounds abstract.
It is a bit. Instead of working in our usual 4 dimensions of space-time, they knew the calculation in, say, d dimensions, where d might be something like 4 minus epsilon, with epsilon being a tiny variable.
Why?
Because often, in d dimensions, those integrals that blew up in 4 dimensions actually become finite. You can manipulate them, perform the renormalization steps to cancel out the problematic parts that diverge as epsilon goes to 0.
Ah, so you sidestep the infinity temporarily, fix the theory, and then go back to 4 dimensions at the end.
That's the gist of it. It's a consistent way to handle the math and arrive at finite physical predictions.
Okay, so QED was a huge triumph.
Yeah.
But what about the other forces? The weak force, the one behind radioactive decay, that caused problems too, right?
It did. The early model, the intermediate vector boson, or IVB theory, proposed massive particles, the W plus and W, carried the weak force.
Sounds reasonable, like photons for EM.
It did, but it had a fatal flaw.
Yeah.
It was non-renormalizable.
Meaning the infinities just kept getting worse.
Exactly. When you tried to calculate higher order corrections, you got new kinds of infinities that you couldn't just absorb into the bare mass in charge like in QED. The theory basically broke down at high energies, a huge headache.
So how did they solve that one? It sounds even worse than QED's problems.
The solution was brilliant, and it came from generalizing the idea behind QED itself. Gauge theories.
Gauge theories again. What did that involve here?
Physicists like Glashow, Weinberg, and Salam realized they could build a unified theory of both electromagnetism and the weak force based on a more complex gauge symmetry, specifically SU2 cross U1.
Okay, SU2 XU1. What does that symmetry imply?
It implies the existence of 4 fundamental force carriers, 4 gauge bosons, but initially the symmetry requires them to be massless.
4 massless bosons. But we know the W particles are very heavy. And the photon is massless. How does that work?
Through a process called mixing. These 4 initial massless fields interact and rearrange themselves. One combination remains massless, that's our familiar photon. The other 3 combine to become the massive W plus WS and a new, previously unexpected particle, the massive neutral Z0 boson.
Wow, so the theory actually predicted the Z boson.
It did. And it also predicted neutral current interactions mediated by this Z boson weak interactions where charge doesn't change hands. These were experimentally confirmed later, a massive success for the theory.
But hang on. If the underlying symmetry demands massless particles, where does the mass for the W and Z actually come from? It feels like cheating the symmetry.
It's not cheating, it's subtle. It comes from spontaneous symmetry breaking via the Higgs mechanism. This is really quite remarkable.
Spontaneous symmetry breaking. The symmetry is still there in the equations, but not in the universe's state.
Exactly. The underlying laws, the Lagrangian, still possess that SU2IU1 gauge symmetry. But the lowest energy state of the universe, the vacuum, doesn't respect the full symmetry. There's this scalar field, the Higgs field, pervading all of space. And in the vacuum, it has a non-zero value.
It's not zero everywhere.
No. And when the W and Z bosons move through this non-zero Higgs field, they interact with it. It's like wading through molasses. That interaction gives them inertia, which we perceive as mass.
They eat parts of the Higgs field, effectively.
You can think of it that way. They absorb components of the Higgs field, specifically the would-be Goldstone bosons, and become massive. The photon doesn't interact with the Higgs field in the same way, so it stays massless.
And the Higgs mechanism does more than just give mass to the W and Z, right?
Correct. It also naturally provides a way for fundamental matter particles, like electrons and quarks, to get their mass through their interaction with the Higgs field.
And it leaves something behind.
Yes. The mechanism requires the existence of at least one leftover excitation of the Higgs field itself, a massive scalar particle. The Higgs boson.
Which was famously discovered years later.
Indeed. Finding the Higgs boson at CERN in 2012 was the capstone confirmation of the standard electroweak theory. It's gauge invariant, it's renormalizable, it correctly gives masses to the WZ and fermions while keeping the photon massless. It's been incredibly successful.
Just amazing. Okay, we've covered electromagnetism and the weak force. What about the strong force? The one holding quarks inside protons and neutrons.
That's the realm of quantum chromodynamics, or QCD. It's another gauge theory, but this time based on a different symmetry group, SU3.
SU3. And instead of electric charge, quarks have.
Color charge. We use the analogy of colors red, green, blue, though it's not literal color, of course. It's just a type of quantum charge.
And the force carriers are gluons.
Yes. 8 types of gluons mediate the strong force between quarks.
And here's where QCD gets really weird compared to QED, right?
Very weird and very interesting. The crucial difference is that gluons, unlike photons, do carry the charge of the force they mediate. Gluons carry color charge.
So gluons can interact with other gluons.
Exactly. They stick to each other. This self-interaction has a profound consequence called asymptotic freedom.
Asymptotic freedom, meaning the force gets weaker.
Weaker at short distances or high energies. It's completely the opposite of electromagnetism, where the force gets stronger as you get closer.
Why was that such a puzzle?
Because naively, you'd expect forces to get stronger up close. Discovering that the strong force gets weaker was a huge surprise, explained beautifully by the theory and the maths of the renormalization group. It means quarks inside a proton, when they're very close, act almost like free particles.
But if you try to pull them apart,
The force gets incredibly strong, like stretching a rubber band that doesn't want to break. This is confinement. You can't isolate a single quark. They're forever bound together.
and QCD has its own mathematical complexities too. Something about ghosts.
Ah, yes, ghost fields. When you try to quantize non-abelian gauge theories like QCD consistently, especially using methods like path integrals, you run into some mathematical issues related to redundant degrees of freedom in ensuring things like probability conservation work out right. You have to introduce these mathematical constructs, these ghost fields. They aren't real particles you can detect, but they are necessary internal components in the calculations to cancel out unphysical effects and make the theory consistent. A bit technical, but essential for QCD to work.
Wow, what a journey. From photons and electrons, wrestling with infinities, unifying forces with these deep symmetries, discovering the Higgs, and finding this bizarre asymptotic freedom in the strong force. It's a lot.
It really is. And connecting it all back, this deep dive really shows how these sometimes very abstract mathematical ideas in quantum field theory give us the most stunningly precise description we have of reality at its most fundamental level. The framework keeps making predictions, and experiments keep confirming them. It's an ongoing triumph of theoretical physics.
So what does this all mean for you listening right now? Think about it. Understanding these deep rules doesn't just let us predict things. It points towards, well, maybe an even deeper unity, a structure to reality we haven't fully grasped yet. What other secrets might be hiding there, just waiting for us to find the right language, the right piece of mathematics to finally see them?